Hi, everyone, and welcome to Valley of Death. I'm your host, Mo Islam. Today, we're tackling one of the most audacious ideas in energy. My guest is Marc Berte, CEO of Overview Energy, a company building space-based solar power. In other words, collecting sunlight in orbit and beaming it as near-infrared light to existing utility-scale solar farms on Earth. Marc's thesis is simple. The world needs far more power, and the grid can't move energy fast enough to where it's needed. We'll get into how Overview's system actually works, as well as how they test its economics, customers, and safety case. We'll also cover progress so far, including their upcoming demonstrations, with the biggest challenge now in scaling manufacturing, not proving physics. Basement lab to grid scale ambition. Let's dive in. Marc, tell us what the core problem Overview Energy exists to solve.
I mean, the simplest way to put it is the world needs more power and the grid sucks. Energy has insane demand and insane constraints, and the grid as we know it, or even as people are proposing, just doesn't move energy fast enough to keep up with the rest of where development is going. And we seek to solve that problem.
And why is now the right time to build, of all the types of energy sources that you can build, to build power beamed from space?
It's kind of twofold. The first is it's the right time. The market exists that requires this kind of on-demand, everywhere energy, and the technology exists, and that's a big difference from 10 to 20 years ago. So it's a combination of those two things. So right time.
And then, so really, the technology exists today to kind of bring this from concept to reality.
Yes. Do you want me to go a little more detail, or
Yeah, sure. No, sure. Okay. Let's jump right in.
I don't want to fill up the whole hour on digging into one piece of it.
No, let's jump right in. Also, I noticed that you're sitting in. You mentioned earlier you're sitting at home where you started the company, right? In your I don't know if this is your garage, or your home office, your bunker.
This is the electronics lab portion of my basement. I have a machine shop and wood shop and that kind of stuff. Yeah, we started down here in my basement, incubated inside of Vast. And then at one point we had 6 or 7 people down here building the core technology. And then we finally got in our actual space when we started, bringing in some large scale external investment.
Okay, so we'll get into the technology piece in just a second, but actually tell us a little bit more about how you came. I mean, yes, time is right, but like, what drove you to want to solve this, pretty ambitious problem?
Personally, I've always been into nuclear engineering and aerospace engineering. I've always been into kind of where the pressure is high and the temperatures are high and the energy density is high, and that's where all the fun is from an engineering perspective. Over time, I worked on a lot of defense stuff, lasers, spacecraft, optics. And over the past kind of 10 years, started getting into energy storage, and what matters on the grid. And there's really only a limited number of ways we can solve the Earth's energy problem, which is basically we need another Earth worth of energy in the next 20 to 25 years. It'd be really nice if that was environmentally friendly energy along the way. And there's really only a few ways to look at it. It's fission, fusion, terrestrial solar plus storage, large scale advanced geothermal, and space solar energy. And space solar energy was kind of the under thought of and underutilized one. It was always this, someday the technology will be there and launch costs will come down. And so looking at it from that perspective, I started looking at this as, okay, well, if you want to solve this problem, how do you do it? Truly, where you have to build a company, you have to capitalize it, you have to do all these things. Like, what is the right way to solve the space solar energy problem? And one thing my entire career has been is kind of A plus B, like what's changed and why is the solution now? And what I realized was if you pick the right path, which is what Overview is doing, is the technology is now available and can be built up to where the required kind of launch cadence and everything is going to be there when you've built the technology to the level required.
Right. Well, I want to take a quick step back because you mentioned you have a nuclear background. Why didn't you pursue fission or fusion?
Well, I am actually kind of doing both. Like, I advise fission companies and fusion companies as a subject matter expert. My thesis was on small modular reactors. We kind of need all of it. And there's an enormous number of extremely smart people and very amazing companies and a huge amount of capital being just poured into fission and fusion. And we need to check all of the boxes of what energy we can do. And one of the really big points is once you build a large fusion reactor or fission reactor, you can't just move it. So like if it doesn't need all that energy, at midnight, it's just, potentially just sitting there, and transmission infrastructure is extremely difficult. So with space solar energy, especially the way we're doing it, you can redirect it all over the planet. So now you can put it where you need it to be. So it's a good mix of both.
Yeah. And then you mentioned incubated and vast. So tell me more about that.
So that's actually a really fun story. So very early on, and this was in the first few months of VAST, Jed and a lot of the others were, okay, well, what do we do in space? And space solar energy got brought up, and a friend of mine was working there and was like, okay, Mark has been working on like the solution to this problem. You need to talk to him. Jed was really skeptical at first, but funded the initial where he was like, okay, prove the physics works on this, this, and this, and this, and then we'll talk. That took about 6 months. He went from being skeptical to being very on board, and then Overview spun out as a separate company. And Jed was our first major angel investor. Vast has a small ownership share, and it's been a really great way to they're checking the box for what they're doing in a very clear and concise way of like just driving to the goal. And it was great to work inside of that environment and then bring it out from there.
Interesting. Yeah, and for those who may not know, Jed is the founder of VAST and has been quite involved within the space industry over the last 5 or so, 6 or so number of years. It's been a bit, but anyway. Okay, so what is all right? Tell me a little bit about. Let's kind of pivot to the technology piece of all this. What is state of the art today that makes this work, and maybe tell me what still doesn't work.
That's the the part that's often missed on this is if you're trying to build to a super large scale, you almost don't want like the perfect state of the art. You want to optimize around the real world constraints. Like what is the thing that actually matters? So I'm going to kind of pivot your question a little bit, which is what is available now that allows you to get to the dollars per watt or whatever, and what's kind of changed. The critical pieces of this is, we use what we call wide beam near infrared from geosynchronous orbit, not geostationary, geosynchronous. So we can go into that later if you want. And so we absorb the light in space, turn it into near infrared light using super high efficiency lasers, and beam that to existing utility scale large solar projects on the ground. So the key things that changed on that is the laser efficiency is now dramatically higher than anyone even thinks nowadays. The receiver solar panels on the ground are now exactly where you need them to be. And really most importantly is this is a demand driver for low cost launch. And thus you can look at this and say, okay, what does launch cost have to be for a given set of technology? So the critical piece is how we're manufacturing all of these things and getting that cost down on that. So does that?
Yeah, no. So no, it does.
Yeah.
It does. And there's a lot of different ways we can take this conversation. So I want to maybe start at a high level. So the core architecture of your system is you have a craft in space that's collecting the energy, beaming it down to a receiver via infrared laser to a receiver on the ground. Is that correct?
Yeah, that's correct.
Okay. Go ahead.
The critical piece is kind of the size of the receiver, the size of the spacecraft. So if you look at classical ways of doing space solar energy, it's always these large scale microwave systems where you have these kind of kilometer class spacecraft in geo you have to assemble. And then you have these antenna farm basically on the ground. Or you have, really narrow beam laser where you're trying to serve, like a Green Beret team in the middle of the woods or something like that. With this, it's kind of kilometer class receiver, and the receiver is just your off the shelf solar project. Like we work with a variety of different commercial partners that are just 100 megawatt, multi-100 megawatt solar projects. And then the satellite in space is deployed, not assembled. So you kind of don't want to solve the in-space assembly problem while you're trying to solve all of these other problems. So does that help and kind of define the?
Yeah, it does. So talk a little bit about the actual uh, acquisition, for lack of better word, collection I'll use of the solar energy, and then the beaming process, and then the efficiency of like how much you're collecting versus how much you're delivering ultimately. That can be that's usable energy, because everyone talks about terrestrial solar panels, like what the efficiency of those solar panels are. And I think if you didn't know anything, you would just kind of assume, okay, the solar panel like are pretty efficient, but they're actually very inefficient in terms of like how much energy that they collect versus their output. So maybe talk a little bit about that.
Yeah, the way to think about that is, how much solar panel do you need for a given amount of energy? Not necessarily power, but energy. So, averaged over the day or year. So, your typical solar panel, yeah, it's 25, 30%. We're getting up there in terms of efficiency, but its capacity factor, how much energy does it make on average, is only about 25% of that. So, 75% of the time, the solar panel on the ground isn't doing anything. Now, in space, you have light 24/7 in geo, except for eclipse season, but, basically 99.2% of the time. So the critical efficiency way to think about it is, does your efficiency of transmission, getting the power to the ground, is that higher than the capacity factor of the panel on the ground? So thus, if you think about it, let's say the panel on the ground is 25%. Well, if the efficiency of getting the energy down is more than 25%, the same square meter of solar panel in space will actually be making more energy than the one on the ground. So you have to look at it kind of systemically. So real quick, kind of the architecture is you put PV in space. So we use low cost cells on this. People are pouring huge amounts of money into making PV efficient and cheap. So we'll leverage that. Turn that into near infrared light using an electrically driven fiber coupled laser, and then using optics, beam that energy to the ground. And what's great is the energy you beam to the ground is specific. The wavelength is specifically chosen to convert super efficiently on just off the shelf solar projects. So you don't have to do anything on the ground in order to make the system work.
How are you thinking about safety, precision, and sort of the regulatory constraints when you're thinking about these high energy beams, which I assume are going to get more efficient and more powerful as you continue to build and progress?
Correct. And I'm really glad you poked at that. That is, especially coming from the nuclear industry and aerospace, those are the hard parts, is, safety and regulatory. Like, how do you take into account those things? And a fundamental piece of overview is passive safety. Okay, so this is, no matter what you do, it cannot be dangerous. More importantly, it also cannot be turned into a weapon. So from a passive safety perspective, you have to look at it as, okay, as an example, you can stand in the beam, you can stare at the beam occupationally, all day long. It doesn't negatively affect animals or plants or spacecraft or aircraft or anything of that. And you have to be able to do that where it doesn't require active intervention. You don't have to we detect something coming into the beam and then turn it off. What you want is, it doesn't matter. You can stand there and it's just fine. You can stare at it with binoculars. It's just fine. So what's great about that is that meshes well with the existing regulatory framework. Okay, so regulatory framework is around, you can hear like class 1 lasers or stuff like that. So our beam is actually safer than sunlight. And from a regulatory perspective, it's lower, intensity or, eye effects or anything like that than even like LiDARs on cars. So that way you can solve that and say okay, from your existing regulatory framework, this fits within it, both nationally and internationally. And that was a fundamental kind of constraint from the very beginning with overview, is that passive.
Got it. Okay, yeah, that makes sense. Is there any? I mean, what regulatory body would you be interfacing with?
It's mainly on the space side. So, we're hoping for mission authorization at some point to kind of, work its way through the legal system. And because we are going to deploy relatively large constellation of these things, on the laser side of things, it falls into a bunch of different groups depending upon the different aspects. So this can be OSHA, this can be FDA, this can be other aspects of that. Telecommunications, and for some international aspects. But it's mainly those kinds of areas.
Well, so now you're not the only person doing space-based solar power. There's a number of other companies, Aetherflux, Reflect Orbital, Tell me a little bit about your approach versus theirs and how you kind of think about competitive positioning.
I think like one of the ways to really think about kind of competitive positioning is both path, like what path is the company taking, but also what is important from an economic perspective. So Reflect uses mirrors in space in Leo to reflect sunlight down to both for illumination purposes as well as to put solar projects for power. So there you're not independently converting the light into something else and transmitting it down. So it leverages different aspects of that overall path. Like what do you have to make cheap? Um, Ether flux is what we call tight beam near IR. So this is having a spot on the ground that's tens of meters, but also, on the order of tens of kilowatts instead of, potentially hundreds of megawatts. Whereas we're in the kilometer scale near IR. They're in Leo, we're in Geo. So the important piece is we're looking to design for grid level from day one. So the economics of this are really important to look at. Can you scale to hundreds of megawatts, gigawatts, significant fractions of the overall grid, as opposed to finding like niche customers for that first of a kind?
Okay, well, let's talk about the economics since you brought it up. How do you think about economics of orbital energy? I'll call it orbital energy versus terrestrial renewables. What's the right comparison set for space solar in terms of like levelized cost per kilowatt hour?
Oh boy, LCOE, like the dominant thing. No, that's really the core idea. Um, One of my chief of staff always jokes that overview was started with a techno-economic analysis, and he's not entirely wrong. The old analogy is, and anyone can build a bridge. It takes an engineer to build one that almost works, or barely works. The real world constraint is actually capex. It's dollars per watt. That's the biggest driver for dollars per megawatt hour life cycle cost of LCOE, life cycle cost of energy. Because there's really no O&M and those kinds of aspects. There's no fuel. So it's really the capex. What you have to do is, how does that fit? Okay, so this is the cost of the launch, cost of the actual system, and then the efficiency aspect of getting it down. And you have to pick the right solution for all three of those. So you could pick a solution that's really efficient, but costs a lot. Well, that, efficiency getting it down, but now you have, this. Or it's really heavy, so the launch cost goes up, and you have to trade inside of that. So what Overview does is our specific approach is designed to optimize around that. So for instance, we put in a huge amount of effort getting like the lasers and optics to where the cost of them is the right comparison to the launch cost. And then, so you don't want to pay for too much efficiency, for instance. You want to get the right efficiency that maximizes the cost. The other thing to really look at is you have to build in failure. You have to want the system to fail gracefully. You're not looking for perfection. That's the expensive part. You're looking for reliability. And one other aspect of this on the economic side is how you treat it with respect to terrestrial things, where this is different. So you're competing on the same kind of piece where it's, okay, energy on the grid. Hopefully it's, base load like, as in you can get it whenever you want. But space solar energy, which is the term we use for this, has this dispatchability aspect where if you're in Geo, you can see a third of the planet at a time. So the ability to move that power to where you need it when you need it is you can think of as different product than any other real form of energy out there. You'll hear a lot of, the grid is very congested and you can't move power around and it takes forever to put in new transmission lines. And that'll still be the same if you're picking fission, fusion, terrestrial solar plus storage, any of the other things. Whereas if you have something where you can redirect the power dynamically from space, it solves that problem as well. So the economics kind of fit two different ways.
Yeah, no, that makes sense. I am curious though, in that example, like, how do you measure? And this might be something that's impossible until it's in practice, but like, have you guys thought about um, what that premium is worth, right? Just to like, because at the end of the day, energy just like comes down to this idea of like how much are you like. I mean, it's like the reliability, like it's reliability, it's the ability to actually get the energy, and then of course there's like ultimately like cost, like what is the end cost, and depending on where you are and what the application is, those priorities kind of change. Like And by the way, this is not my area of expertise. I'm just talking about it out. Like I'm just kind of thinking through all this out loud. So, so correct me if I'm wrong on any of this stuff. But I am very curious. Um, like how do you kind of measure what that premium should be in terms of like, I mean, we're entering a world where you have all these different power sources. Battery technology is getting better, storage technology is getting better and better to help kind of solve some of the issues that renewables have had for quite some time. So how do you think about like how much more someone should be paying for this?
Okay. Um, that was a lot to pack in there. So
Yeah,
I'm gonna
sorry.
have to, no, no, it's great. I love it. I'm gonna have to kind of deconvolve that question a little bit. First of all, it isn't what someone should pay for it. Like we have a market, it's what people are paying for it, and we want to reduce cost and improve energy equity and all these things. And so you're hitting on the right thing in that the cost is the key. A good way to look at this is energy mixes all over the place. We have dynamic energy markets. There are cases in like South Australia where energy can be 100 times the normal average price for a few hours, and a battery system will make all its money right then. Um, Small grids tend to cost more than others. If you look at, for instance, the United States islands, so Guam, American Samoa, Hawaii, U.S. Virgin Islands, Puerto Rico. Okay, pay 5 to 10 times the national average on average for their electricity. And it's because getting energy there is difficult. You don't have large area wind farms. You don't have all these kinds of things. Um, Even in the United States, if you just throw a dart at any given time, you could probably find instantaneous energy that's 3 to 4 times as expensive as normal. So the premium, we already know it's in the market. So as just a real quick example, if you look at the United States, the wholesale average price of electricity in the United States is like $50 to $60 a megawatt hour. Okay, you can go. I don't want to like quote a website, but I think gridstatus.io is a good one, and you can see instantaneous electric prices all over the country. And it's not hard to find 100 almost all the time somewhere. Okay, so and that's
And that's a number that makes your economics work.
yeah. You really want, if you're trying to do grid level, what you want is your cost to come down as you build more and as you get more efficient and launch cost comes down and everything. You want that to match your available market. So early on, you want to find, in our case, hundreds of megawatts of demand that is at potentially, say, hundreds of dollars a megawatt hour. So this is the U.S.
Okay.
islands. Remote air bases. So this isn't like some guys in the jungle. It's, an Air Force base kind of aspect where it's tens to hundreds of megawatts. Then for your next stage on that is, high demand areas. So the UK is one of these where prices on average are quite high, but still a little lower. And then you work your way down that curve. The actual curve, if you want to look at it, is for every factor of 2 in terms of electrical cost, you end up with about 10 times more demand. So, like, if you look at the globe, it's, terawatts, but it's like $50 a megawatt hour. Well, you get hundreds of gigawatts at $100 a megawatt hour. You get tens of gigawatts at, as you work your way up that curve. So what you want to do is pick a technology that scales down that path without any kind of discontinuities. And that's really what we're doing.
So you mentioned islands, and a lot of those islands are military bases. So is your first real customer on the DoD side? Tell me a little bit about what you think your first real customer looks like.
I wouldn't say it's a customer. It's always a mix. The military goes in kind of feast or famine, and also when their demand is. So if a lot of stuff is going on, there's a huge demand. But then in relative peacetime, there's more stable demand. And it isn't just a military base; it's the military base and the people around it that support that military base all have power demands. I would say our first customer is likely a mix of like large scale military bases plus high demand, like temporal demand kind of things like data centers. It's obviously the AI boom is happening and there's a significant amount of demand on that. But you want to mix these all together. Um, so, as an example, it's the time part that matters more than the which customer. So, as an example, if it's 5 p.m. in Northern Virginia. The electrical demand is skyrocketing. The price is extraordinarily high. But if you go to Kansas at the exact same time, it's extremely low. It's early afternoon, not a lot is going on. The wind is pretty good. There's a huge amount of wind power there. It might even be negative pricing. So, what you want is a mix of customers that hits all of those things. So, some military bases, some peak demand kind of data center aspects, and then the beginnings of your big commercial flow. So, what are your large scale customers you're going to start addressing earlier and mix those all together?
Okay, so let's just talk a little bit about sort of the infrastructure required on your end for this. Like, and let's mix that, sorry, let's map that to like your kind of go-to market strategy as well, which is like to be able to do this at all these different locations. I'm assuming you're going to need the receivers that you've mentioned earlier, like placed around all of these locations, and you need sort of the infrastructure to be able to plug those receivers into the grid that allows it to then be used as energy. Um, like, what does that look like? How are you thinking about where to build that infrastructure first? Is it totally dependent on the initial dollars of like who's willing to pay for it? Like, how are you thinking about that infrastructure build?
The part that's kind of missed on this is that
Yeah.
infrastructure is already there.
Okay.
So because
I did miss that.
yeah, so we did, yeah, no problem. And that's a real critical part of overview is the receiver on the ground is a utility scale existing large solar project. Okay, so you pick your drive around in the desert, you see, square kilometers of solar arrays. That's our customer. If you look at, even on the order of about a kilometer, so you're looking at 100, 200 megawatt size things. There's literally tens to hundreds of these in the United States already. All that is required for them to be part of what we see in the future as kind of an overview network is we have an upward transmitting invisible near infrared beacon. So you put this beacon, it's about the size of a shipping container, you put it in the center of the solar project, and now that is what the satellite uses to aim. So that process, and there's a whole bunch of optics and tracking and everything that goes into that. That's actually the hard part. The lasers are the easy part. The tracking and everything is the hard part. Uh, so we don't have to pick where the demand is, even for the initial customers. It's already being demonstrated by people installing these projects.
Interesting. Okay. And then when you think about the economic sort of the kind of economic drivers or bottlenecks, I think you mentioned it earlier, but like is launch the the biggest driver for you?
No, good space question from the space podcast. So yeah, it is. Launch is the one that's it's outside of our control, other than creating demand. And it was the last thing that I was waiting for before starting overview. In effect, we were waiting for line of sight where is this going to be high cadence, high volume, low cost within the next 5 to 10 years. And when Starship started, when they did Hopper and when they started, pushing down the Starship program, and then most importantly, others as well going into the high launch cadence, low cost push, between Rocket Lab and Stoke and Relativity and Blue Origin. Like everyone is now pushing to this. Oh wow, there's going to be huge volumes going into space. That's really the last piece where space energy now becomes worthwhile. What I think is the bottleneck there is all of those things rely on a huge demand signal. Okay. So, if there wasn't a demand for a million F-150s a year, trucks would be probably a lot more expensive. So I think space solar energy is the flywheel that could drive that in the long run. In that, if you think about trying to power the Earth, that's a lot of launch. We joke internally, it's like at a certain price, we will buy an infinite number of an infinite amount of launch capacity. And I think every other space solar energy company would say the same. So, but yeah.
Do you think launch costs today are where they need to be to kind of kick off that flywheel?
I would say I don't want to get into like proprietary or any of that kind of thing. I think if you went to SpaceX and booked a Starship, okay, so for 2028, 2029, I don't know what exact dates they're booking them for, but people are starting to book them. you would probably get prices that would support some of those early customers that we're talking about. With our technology at the kind of first of a kind level, we believe we have marginal profitability, so on each individual spacecraft, at launch costs that are in the high hundreds of dollars, if not around $1,000 a kilogram. Which, if we don't have that in 3 to 4 years, no, I think we're probably doing something wrong.
Do do you have customers kind of like signed up, any LOIs, any type of like commercial, any type of traction so far that you can share?
I'm not going to share names. We have, because of certain agreements, we have several main LOIs in place for utility scale. We have one big IPP that we're working with directly. And we have a pipeline for both IPPs as well as a pipeline to get some hyperscalers on board. We don't have any of the signed agreements with that yet, but we're working towards that. It's less about securing those right away than it is the potential. So, for instance, customer journey. When we talk with a solar developer or IPP, what we're most concerned about is, what do their facilities look like in the 2028, 2030 kind of time frame? So, are they optimized for what we would be able to deliver? And how does that fit with their overall path forward? So we want to target our capabilities to the customer. So, what beam size does this need to be? What kind of panels is it? All those kinds of things. But the pipeline is actually pretty robust. There's, many tens of potential large scale customers in there.
And curious, like, how are you engaging? We talked about the DoD. How are you engaging with like the DOE or like NASA when it comes to testing or validating the systems?
So, in both of those cases, the interaction is more along the lines of, okay, well, what is needed to prove this in terms of capability? So, like with DOE, it's, we talk with folks at NREL and stuff like that, where it's, okay, how does this interact with the grid as we know it? And we do a significant amount of internal modeling on that. We've developed some tools to kind of see what the impact is. So there, the DOE is more, oh, now we have to think about space solar energy. It was just a thing that wasn't part of the mix. So, and you have to treat it differently because of this redirectability. So this is now really the beginning of a lot of those interactions of, oh, wow, we have to actually think about space solar energy and how it impacts the grid. So we're starting up some significant work with the DOE on that. On the NASA side of things, we have former NASA directors on our advisory board, and how we're interacting with them. And there, we're learning a lot of lessons from NASA, and a lot of our early demonstrations are, what can we leverage there, whether it be test facilities, SpaceX kind of things like that. But in most cases, we're really focused on the commercial side, other than some niche applications with DoD. The thing about overview is you have to look at the large scale, and that's really what we're doing. We're concerned with hundreds of megawatts to gigawatts, and even the DoD as a whole, the energy demands are at the lower ends of those kinds of levels. So, but that's really the interaction, is what can they do to support this?
What type of tech demonstrations and early proof points have you had around the technology?
Well, it's a journey. So that's the thing, is we always like to say, we're solving the boring hard problems. And so, you can make flashy demos and those kinds of things, but I always ask the team, and then what? What is it after the demo? Did you learn something? Is this along the path? Just as an example, we have a significant ground program that we're doing. So we've done transmitted, the lasers are multiple thousands of watts over tens of meters, and testing the tracking system where it has to, maneuver itself and do all these things that are the actual difficult parts, which is, transmit this from a moving target. We're now right in the middle of a very substantial airborne test campaign. So this is where, using the same methodology we're using in space, so same types of optics, same types of lasers, same types of beacons, same system, and same functionality that we would use in space, we're now testing from an aircraft. So we fly an aircraft at around 16,000 feet. We circle a small solar project that has a beacon installed in it. It tracks the beacon. We, fire the lasers. And this is an ongoing thing. We've done a bunch of tracking flights over the next few months. We're ramping up our power levels on the system. Um, and the critical piece there is, we want to make the difficult boring. That's really where you want to get from a grid level and to optimize this. So a lot of actual progress on there.
To talk about, okay, so that's awesome, by the way. That's super exciting. When will you have like a space-based demonstration?
So we're actually booked. So the first Leo demonstration. So this is a Leo bird that tests it. You can think of it as testing one slice through our modular GeoBird. So same kind of tracking, same large scale optics, same lasers, same radiators, same solar panels. That we're booked to fly on Bandwagon 7, which is January, February 2028. So we're booked on that. Then we hope to follow that with our first GeoBird in 2030. And what's really critical is that GeoBird. So that's megawatts. So the race really isn't to, kilowatts from Leo. The race is megawatts to Geo, because that's when it unlocks the large scale market. So we're really focused on that and see Leo as this demonstration. You have to do in space before you can do it big in space and work your way
Got
through
it.
that.
Okay, makes sense. Let's talk about China, because I'm curious what your perspectives are on there. Like, is China investing in heavily in orbital power? They're trying to compete with us in all sorts of elements of the space race, space industry. How, how much do you know about what type of work they're doing within sort of orbital energy?
They're heavily investing in it. As you said, this is a global competition for increased energy levels and increase everything. China has a very substantial national program. They're focusing on two or three things. They're looking at microwave transmission from orbit, your classical kind of large scale space solar energy approach. They are looking at some tight beam laser power beaming aspects too, in the same kind of vein of what we call tight beam near IR, like the ether flux kind of aspects. And they're also looking at space to space power beaming. So this would be the example in the US would be StarCloud, or not StarCloud, sorry, Starcatcher. StarCloud's a data center.
Yep. Sure.
Starcatcher doing space to space power beaming. So they're kind of hitting all of the different areas of it, but it's big, and this is a global competition. There's European programs, there's Japanese programs. This is 2 years ago, space solar energy wasn't an industry, and now it is. So it's a great time to be there.
I know you have a great selection of investors who are backing what you're up to, and of course, Jed being one of them. How much have you raised so far?
So we raised a little over $20 million. That was through a seed and seed plus round. We're going to be raising more in a new upcoming round now that we're coming out of stealth after several years of concentrating on the long-term problems. And we're the mix of investors on that is everything from climate focused investors to like infrastructure and large scale energy investors, and the whole mix. We're really targeting that grid level and what that takes in the long run.
Got it. And can you share how much more capital you think you'll need to get to that first watt of power from Geo?
That's actually a very difficult question, and also not just in terms of um, what the actual number is, but I think the way to look at that is from a capital efficiency standpoint. Overview and the technology associated with it was really designed around minimizing, the U curve. Like, how much capital do you need before you can start bootstrapping in? Our goal for that was, if you need to be able to get into marginal profitability at scale for under low single digit billions. Um, that was our goal. We believe that that is entirely doable with the technology approach that we have. So I would say in the hundreds of millions, but definitely not in the plural billions. What really will define that is actually the next year. We're focusing on our manufacturing and scalability stuff. So we're starting to really start building things in quantity. And that's really going to define how much that kind of last stage is to get it into, multiple satellites on orbit.
Where are you building out your factories?
Well, so That's somewhat up in the air for the large scale production. We're currently based in the Washington D.C. area, and so our initial design and development and initial production line, those kinds of aspects are going to be in the Washington D.C. Northern Virginia area. For the larger scale factories, we're talking with a bunch of different folks as to where those should be based. Your classical, Texas, Florida, like launch is an important factor for us. And it's, near equatorial launch, so probably not, Vandenberg. And what that supply chain looks like is really going to be critical. So we're talking with a few different providers, but it's probably in the long run, Texas and Florida are both really good examples, but I don't want to narrow it down too much for the large scale.
Got it. Okay, great. I have a few sort of like future outlook, kind of big picture questions that you're an energy guy, and I would love to dig into for just a few minutes. You might yell at me for this first question, but I'm going to ask it anyway. Do you think terrestrial renewables can ever meet global kind of base load power needs without space-based energy?
What do you put in the renewable category, I guess? Like, do you put fission and fusion in the renewable category?
No, well, no, I don't. Like,
Okay.
Let's just use solar, wind, hydro, and yeah, solar, wind. We can just keep it solar, wind, because those are obviously the two biggest categories.
I mean, unfortunately, that's a very complex.
No, for sure. I know it's a complex question. I just mean, like, look, at a practical level, right? We can't put solar panels every single place on Earth. Like, there's a practical piece of all this, right? Which is like, could we theoretically can versus like, can we practically can? I think this is more my question.
Okay. Yeah. That's a really good way to put it in terms of, theoretically you can. You can make it work if you have sufficiently dispersed wind, if you have, sufficient solar with sufficient storage. Yes, you can do it. There's plenty of studies out there. From a practical perspective, there's, kind of 3 or 4 things that really drive this, and I'll try and get through it real quick. It isn't like the cost of storage, for instance, that drives you on solar plus storage. It's the amount of overbuild you have to do on the solar so that you can average a certain amount. What we call the January day problem in North America, where you might only have 6 hours of sunlight. So now you not only have to charge batteries that get you through it, but you have to power it during the day. And the amount of overbuild really starts driving it to get that reliability aspect. It's the black swan events that end up driving a lot on that, where, you can see these kinds of things where the first 20% of renewables is relatively easy. The grid has a lot of elasticity built into it. The dispatchability doesn't matter all that much. I'm too bad you didn't put in nuclear. The bottom 20% of the US grid is just nuclear at 100, they're just running full throttle all the time. And we don't have to worry about the bottom 20%. It's that middle part where you're running out of grid elasticity. The robustness needs to be in the supply, and you're driving into that area. So you need to do these massive overbuilds. So practically that really starts driving it, because then you're building bigger and bigger solar projects in less optimum locations. And so practically, I think it is somewhat limited. And the other piece is it takes a lot of space. And we're starting to run into that constraint even now where, we need to build, 300 square kilometers of solar projects. Okay, where? Where can you do those kinds of things? So I think practically.
So then, paint me sort of the picture of like what the grid of the future looks like when orbital power becomes a real input. Like, what is that grid of the future? And I won't put a time period on you and 10 years or 20 years. Just let's just say the future.
Okay, I think it's going to look in some ways a lot like it is now. You're going to have large fixed power plants. Hopefully there'll be, advanced fission, fusion, dispersed, advanced super powerful geothermal, terrestrial solar plus storage. You're going to see that kind of conventional mix, but it's going the spatial part of it. The where you put it when, I think, will be taken over more and more by space solar energy. So it's, okay, well, I always say, the Earth needs another Earth worth of power in the next 25 years. It'd be better to build one Earth worth of power in space and put it where you need it to be instantaneously than to have that peak to average problem where you have to build twice as much as you actually need on average. So it's going to look a lot like today, but the large scale transmission, I think, will be taken over by instead moving the space solar energy to where you need it to be. So it'll be a mix.
And right now, what's the biggest technical unknown that'll kind of determine whether this industry works or doesn't?
Well, I can comment on the overview side. I don't know the detailed technical issues for others. For us, we've solved the physics stuff and we've solved the, build at least a one of stuff. Scaling and manufacturing is the hard technical part. Ironically, it's the making it boring is the hard part. It's, launching rockets into space. We've been doing that for decades, but it took a lot of critical technical effort for SpaceX to almost make it boring, in terms of, oh, the rocket landed again. There it is, reused again 30 times or whatever it is. And that's the hard part. It's reliability. It's how, the network can fail gracefully. It's all of those pieces. So we pour an enormous amount of technical work into how do we make this thing cost less? How do we make it cost less and be as reliable? And that's actually the really exciting part. A real quick one, we needed optical laser coatings to be 100 times cheaper than you can go get them now. And we thought that was going to take a huge amount of time. And it turned out we actually accomplished that earlier this year. But it's those kinds of things where, it isn't the glamorous, oh, look at this one shot demo kind of thing. It's okay, now do it a million times. And that's actually the exciting part.
Amazing. Okay, well then, all right. Let's. I'm going to go off on a limb here and say that you're probably a sci-fi guy. You're into like science fiction. So, what is the long-term vision for overview energy, and is it confined to Earth? Are you thinking about the technology's use case off planet and other locations where, like the moon, where energy is also a big problem, and obviously NASA's trying to solve it with fission surface power, and as something that's more efficient than other potential use cases? Or I don't know, like what do you think? Is this a technology? Is this on your mind right now? I guess maybe I'll ask it that way.
I mean, on my mind, I have to focus on, the critical things that we're doing right now. But, if I, imagine, the world decades from now when my daughter has grown up or things like that. The neat thing about space solar energy is it works in space. And more importantly, if the thing you need power on has days and nights, you're always going to have this problem. And space solar energy does solve it. It removes the location constraint of where you need and want to use the energy. Some places are like Mars and Earth are easier than the moon just because where the synchronous orbit is and the day-night cycle timeframes and things of that nature. The moon's actually a really hard problem in this. But yeah, this is, I mean, if you think of even just classic sci-fi, like capturing more and more of the sun's energy, not just on the surface of an object or of a body, is the end state goal. Whether you're Kardashev level 2 civilization or whatever you're going to be, whatever your science fiction, the more energy you can capture and utilize, the farther you're going down that tech tree. So yeah, I think it's applicable. It's great for Mars. So like, hopefully we'll be there as well.
And I just have to ask, because you brought up something that made me think of this. Like, what about redirecting the power to other assets in space?
So there's a lot of companies already looking at space-to-space solar power. In a way, our singular focus is grid scale. And you have to look at technologies that way. It isn't, oh, this product is good enough, and then you can scale it to this. The technologies you would use to power a satellite are almost fundamentally different than you would use to power the grid. You're going to need much tighter beams. You're going to need different safety aspects to it. You need to track different targets. And I've always been one to focus on what is the core problem you're trying to solve and drive towards that, and bring along the right investors and the right customers and the right partners that see that as the goal, as opposed to, okay, is this a good, offshoot along the way? And that singular focus, I think, is really important for this. So we do talk to these groups and everything like that. There is a community associated with power beaming. And I think like there's technologies being developed both inside of Overview, but also inside of all these other companies that will lift all boats eventually, that rising tide. So there's a lot of commonalities, but a lot of difference in, focus and the economics and who the customers are.
Despite my valiant efforts to shift your focus, it just didn't work. So I
No,
appreciate that.
we're aiming for the whole grid,
Yeah.
and have been doing that for quite a bit now.
Okay, well, Mark, this has been wonderful. I am very curious to know, when you're not building overview, what are you doing? What do you spend your time?
Well,
I assume you're very limited free time.
yeah. I have an 8-year-old, so that takes up 8-year-old daughter, so that takes up a lot of my time, and I teach her all the space stuff and everything. My hobbies before overview were car and motorcycle racing, so I haven't done that in a long time, but I would like to get back into that. Still engineering, it's always fun. But yeah, so I build stuff, or all different kinds of things. So it's a lot of building and racing, I think, would be the two big things I do outside of work.
I guess I shouldn't really be surprised. There's a number of you guys out there, founders, CEOs, who are building great companies that are love car racing. So I love it. There seems to be a growing community.
Well, it's operating at the edge, whether it be, engineering racing engines, or operating at the edge, driving them. Motorcycle racing, you're at the edge. You're putting your knee on the ground at, 150 miles an hour. I like it because you can't think about all the other stuff. Like, you have to be in the moment. You have to be singularly focused. You have to have that drive. Otherwise you're, sliding down the track at 150 miles an hour. So, but yeah, right. I think that's why that happens.
Yeah, amazing. Well, Mark, thanks so much for being on the show. This is wonderful, and I appreciate you working with my questions, which were a little bit all over the place. I think you handled them great. So thanks so much for being on the show.
Indeed. Thank you very much.
Okay, until next time.